Hi, my name is Su Sun. I'm a PhD student at the University of Tübingen. I'm very happy to present our work on Attri-Net, an inherently interpretable multi-label classification method using class-specific counterfactuals. Our paper on the same topic will be present at MIDL 2023. Interpretability is essential for machine learning algorithms in high-stakes application of healthcare. However, current deep neural networks are black boxes. Despite their high performance, the black box property hindered the deployment of machine learning models in clinics. Therefore, the goal of our work is to overcome the black box nature and provide explanations for the model's prediction. There are many methods that are trying to achieve this goal. For example, the post-hoc explanations I show here indicate the positive contribution of each pixel to the individual classification decision. However, the post-hoc method tries to explain already trained models, and recent research has shown that they may not be faithful to the actual decision mechanism. In contrast to the traditional classification models, which only predict class labels and need post-hoc method to provide explanation, we design an inherently interpretable model, Attri-Net. The decision mechanism of the inherently interpretable model is directly revealed to the users. Therefore, the explanations from Attri-Net are, by definition, faithful to the decision mechanism. In the following, I will give a brief introduction of how Attri-Net achieves inherently interpretability by splitting the classification problem into two parts, generating class-specific counterfactuals with the class attribution generator and making decisions with simple logistic regression classifiers in the classification layers. Given an input X-ray image and a set of diagnostic tasks, the class attribution generator generates a set of class-specific attribution maps based on the input. Here, we adopt a task embedding layer to generate task-specific vectors to control the output of the generator through adaptive instance normalization layers. With this, the class-specific counterfactual-based attribution maps are generated for each disease. The classification layer consists of simple logistic regression classifiers for each disease. The input attribution maps are first downsampled with a factor of 32, and then the logistic regression classifiers make predictions solely based on the attribution maps. Attri-Net provides users with both the predictions and the attribution maps as explanation. Since the counterfactual attribution maps are human interpretable and the logistic regression classifier is interpretable model, Attri-Net is inherently interpretable. Now let's have a look at the results of classification and interpretability. On 3 large chess X-ray datasets, Attri-Net achieves comparable classification performance with a black box model Resonate as well as the state-of-the-art interpretable model Counterfactuals. We evaluate the interpretability of the explanations qualitatively and find the explanations from Attri-Net are consistent with human knowledge and correctly locate the disease-relevant regions. We evaluate the explanations quantitatively according to the class sensitivity metric. The class sensitivity indicates that the attributions for disease-positive images should be different from disease-negative images. As we show here, our model outperforms post-hoc methods and Counterfactuals in terms of class sensitivity. In summary, Attri-Net is a powerful multi-label classifier. The explanations from Attri-Net are faithful to the model, human interpretable, and class-sensitive. The next step of our work is to further evaluate Attri-Net in the actual human machine learning collaboration settings to test its real usefulness in clinics. Thank you very much for your attention.